Hello, everyone, and welcome. Today, I would like to talk about validate binary search tree. A valid binary search tree is defined as follows. The left subtree of a node, so will be 1 here, contain only nodes with key less than the node's key. So 1 less than 2. So both 1 and 2 are keys and 1 less than 2. The right subtree of a node contains only nodes with key greater than the node's key. So 3 greater than 2. So it may seem to be trivial to you at first. You just compare each node to their parent recursively. But how about their grandparent node's key? When 5 compared to 1, this part seems to be valid. But when 5 compared to 4 is invalid. So how do we do that recursively to validate the whole binary search tree? Here's a little bit more information about binary search trees in general. Basically, binary search tree is built upon the binary search algorithm. It has a search time of O log n, very fast. If you would like to know more about binary search algorithm in general, please feel free to watch my other video in this channel about binary search. On the other hand, there's a concept called in-order traversal, which traverses the nodes from the left subtree first, followed by the root node and then the right subtree. So subtree, node, subtree. Importantly, in-order traversal provides the node's values in ascending order. Here's an example I would like to use to illustrate binary search tree. Remember, the essence of binary search is that it reduces the possible search range by half at each iteration or recursion. The search begins with a range from negative infinity to positive infinity. Let's say your items are already sorted in a ascending order, then we want to begin the search with the middle item within this range. So that will be item 4 with key equal to 4. And it only has one single count. So this is what this node is all about. At the next iteration, we want to reduce the search range by half while excluding the parent node's key itself. So you have this left half range, and the range is from parent's left to parent's key, excluding. And while you have this right half range from parent's key, excluding, to parent's right. Next, we want to locate the middle item within each of these two halved ranges respectively. And we also have this left link point to the left child node and right link point to the right child node. At the next iteration, we want to halve the search range again while excluding the node itself. And next, again, we want to locate the middle item within the half search range if that item is available. Next, we can further halve the search range again. So the left search range will be between negative infinity and 1. But there's no item available here. Therefore, the construction of this left subtree from this child node ends right here. Through this process, we have constructed the whole binary search tree. Importantly, each of the keys falls within a halved search range. It's halved by the parent, and which is exactly why binary search tree can be so fast with a time complexity of O log n, as we decrease the possible search range by half with each iteration or depth. And this property, uh, the search range, is how we are going to solve this question. Importantly, to validate the binary search tree, we'll use the half search range here for the left link and for the right link. We're going to do this recursively from the top node, the parent node, to the bottom node, the child nodes. Here's an example of an invalid binary search tree. As you can see here, this node has a key equal to 3, but the valid search range is between 4 and 6. So the key falls outside the search range. Therefore, the whole binary search tree is invalid. With all the background knowledge introduced, now let's write the code. So first of all, we're going to add two arguments for this function is valid binary search tree. We have this left limit equals to the negative infinity to begin with, and the right limit will be specified at positive infinity. And then we're going to think of the terminal leaf node first. So by the end of day, if root is none, then we return true. Next, we test the current node to see if it's valid or not. So if the left limit greater than or equal to root value, or root value greater than or equal to right limit, that we know is invalid, and we return false here. Otherwise, we return the function by calling itself again. So we return itself dot is valid binary search tree for the root left, and we're going to do the same thing for our right subtree is valid binary search tree root right, and we use the AND logic here because it takes both subtree to be true or to be valid for the whole binary search tree to be valid. And now we're going to specify importantly the left and right limit as half by the parent node. So the left limit here is still the left limit, but the right limit now is set to the root value. For the right node or the right child node, the left limit will be set at the root value, while the right limit will be the root value, root right limit. So, and that's it. That's our code for this question, and we're going to test how it works. So submit, pending, and done. So let's see the result. It's about 40 milliseconds. It's good. So finally, we'll analyze the code for complexity. So since we need to traverse through each node in this binary search tree, it has a time complexity O(n), and also for the space complexity, since we have this stack in the binary search tree traversal or recursion, right? So due to the stack in the recursion, so we have a ON space complexity as well. And that's all for this question. Hope you find this video to be useful. Please stay tuned and subscribe for more videos. And hope to see you next time. Goodbye.